Let's talk about electricity. It is, without a doubt, the invisible force that powers our entire modern world. I mean, think about it. It's everywhere all the time. But because we can't see it, it's easy to forget just how powerful and how dangerous it can be if you don't treat it with respect.
And that's really the heart of it, isn't it? You never actually see the electricity. What you see is the light bulb turning on. You feel the heat from a stove. You see the motor spinning. It's all about the effects. This kind of makes it feel like magic, but it's pure science. And understanding that science is the key to controlling it safely.
So that's what we're going to do here. First, we're going to pull back the curtain and look at how this whole thing actually works. Then, and this is the crucial part, we're going to talk about what happens when things go wrong and how we can make absolutely sure they don't.
Okay, so to really get a handle on electricity, we need to understand three core ideas. And maybe the best way to picture them is by thinking about something we all understand: water flowing through a hose.
First up, we've got voltage. You can think of voltage as the push or the pressure in the system. Imagine a big tank of water. The pressure at the bottom of that tank is just sitting there, ready to push water out. That's voltage. It's the potential energy waiting to make things happen. And we measure it in, you guessed it, volt. Next, we have current. So if voltage is the pressure, current is the actual flow. It's the amount of water moving through that hose. In electrical terms, it's the number of electrons flowing past a certain point. We measure this flow in amps, or what most of us just call amps. And the last piece of the puzzle is resistance. Every material has some opposition to the flow of electricity. Going back to our hose, a big, wide-open fire hose has very low resistance. Water just gushes through. But a tiny, narrow coffee straw, that's got a ton of resistance. We measure this opposition in something called ohms. Now, here's the cool part. These three things, voltage, current, and resistance, are all tied together by one beautiful, simple formula: Ohm's law. As you see here, voltage equals current times resistance. They're in a constant dance. If you crank up the voltage, the pressure, but the resistance stays the same, well then the current, the flow, has to go up. It's the fundamental rule of the game. All right, so we've got our key players: voltage, current, and resistance. But on their own, they don't do much. To make them useful, we have to give them a path to follow. And that path is called a circuit. See, for electricity to actually do something, like light up a bulb or power a tool, it needs to make a complete round trip. It has to flow from the power source through the device and then all the way back to where it started. It needs a closed loop. If you create a gap anywhere in that path, everything just stops. So to boil it all down, every working circuit needs these four things. You need a power source to provide the voltage, the push. You need conductors, usually wires, to give it a path. You need a load, the thing that's actually doing the work. And it absolutely has to be a complete, unbroken loop. So far, we've only talked about the path electricity is supposed to take. But here's the thing about electricity. It will always take the path of least resistance. It'll take any available path to complete a circuit. And that brings us to the most serious part of this conversation. What happens when that path is you? And this is where we shift gears from simple physics to life or death safety. Because unfortunately for us, our bodies, which are mostly water and salt, can be surprisingly good conductors of electricity. This image shows the absolute worst case scenarios. Whether the current travels from one hand to the other or from a hand down to a foot, that path cuts right through your torso, right through your heart and your lungs. In that moment, your body accidentally becomes the load in the circuit, and the results can be devastating. And this right here, this is what makes it so incredibly dangerous. When your skin is dry, it actually has a pretty high resistance, which offers some protection. But the moment you introduce water, whether it's sweat or rain or just damp hands, your skin's resistance absolutely plummets. I mean, look at those numbers. And what did we learn from Ohm's law? When resistance drops, the current skyrockets. That's what turns a small shock into a fatal one. So how much current does it actually take to be dangerous? You might be imagining a lightning bolt, but the truth is, it's a terrifyingly small amount. We're talking about tiny, tiny fractions of an amp. Just look at this. We're measuring in milliamps. That's 1,000th of an amp. At just 10 to 20 milliamps, you can lose control of your muscles. That means you literally can't let go of the wire that's shocking you. A little higher, at 30, it can paralyze your diaphragm and you can't breathe. Anything above that, and we're in deadly territory.
Let's just focus on this one number for a second, 75 milliamps. To give you some perspective, that's less current than what's needed to light up a single old-school Christmas light. That's it.
At 75 milliamps, that tiny amount of current, if it passes through your chest, can completely override your heart's natural pacemaker. It's called ventricular fibrillation. The heart muscle just starts to quiver. It flutters instead of pumping. And if that happens, it's not pumping any blood. It's fatal in minutes without a defibrillator.
And this quote just drives the point home. It's not about the size of the spark. It's about the amount of current, and crucially, the path that it takes through your body. If that path crosses your heart, the danger is as real as it gets.
Okay, I know that's all incredibly scary, and it should be, but here is the most important message of all. Nearly every single electrical accident is preventable. It's not about being afraid, it's about being smart and respecting the power you're dealing with by using the right safeguards. So how do we stay safe? Well, it boils down to these core ideas. Insulation, that's just the rubber coating on a wire, creating a barrier between you and the electricity. Grounding is brilliant. It gives electricity a super easy, safe path to the ground that's way more attractive than going through you. You've probably seen GFCIs in your bathroom. They're the outlets that constantly check for tiny leaks of current and can shut off the power in a split second. And lockout/tagout is a non-negotiable procedure for professionals. It ensures a circuit is physically turned off and locked, so no one can accidentally turn it on while it's being worked on.
And just one last hazard to be aware of, the electric arc. This isn't a shock. This is when high-voltage electricity literally jumps through the air like a bolt of lightning. It creates an explosive flash that can be hotter than the surface of the sun, causing horrific burns even if you're standing several feet away. It's a powerful reminder of the raw energy we're trying to control. So at the end of the day, what's it all about? We have all these amazing safety devices, insulation, grounding, special circuit breakers, but they're not the most important safety device. The most important one isn't something you can buy. It's knowledge. It's understanding how this invisible force works. Because when you understand it, you learn to respect it. And that respect is what will keep you safe.